Welcome to Algebra 2. Today we've got section 7.1 on inverse variation. All right, so variation means that our two variables, typically x and y, have a special relationship. They follow a pattern. And the first type of variation is a direct variation. So how you can see that is if you hear direct variation, or as you can see in quotes, y varies directly with x, then it means that we have a relationship where our y value is equal to some scalar multiple times x. Okay, so that k just represents that constant. It is some number. Now, an inverse variation is one that follows a pattern y equals k over x. So now that x is not in the numerator, just like y. Now it's in the denominator on the other side of the equation, and we still have that k. And in either case, that's referred to as the constant of variation. Notice how we could see an inverse variation. You may see in the text something varies inversely with something else. In this case, y and x. Okay, now I'm just going to extrapolate a little bit on a direct variation. If we have y equals k times x, if I divide both sides by x, it means the quotient of y over x is always that constant. Likewise, in the inverse situation, if I multiply both sides by x, I find the product of y times x is constant. So those are some tests that we can use to see if a data set that we're given is demonstrating a direct or an inverse variation. Okay, so in the first example, tell whether x and y show a direct, inverse, or neither variation. So number 6, let's take a look. Here I've got 4 times x equals y. Well, as I look at that, I think y equals 4 times x. 4 is that k variable. I don't see x in the denominator or anything like that. So y varies directly as x. Typically, it's easiest to try and solve for y in these cases because that's how we're used to seeing y equals k times x or y equals k over x. That just, I don't know, for me, it makes the most sense. It gives me the best look. So for number 8, if I were trying to solve that, I would get y equals 6 minus x. Well, subtracting away, that doesn't show me a constant multiple, and it doesn't show me dividing over my x term. This is showing me neither relationship, neither variation. And for number 10, here I've got x times y. Well, if I divide both sides by x, I find that y equals some number 1/5 over x. That is an example of an inverse variation. So again, solving for y gives us the best look at what type of variation we have. All right, example 2, here we're looking for patterns, right? We're combing through some data that we're given and trying to find a pattern. And the key is, how do we tell if we had a direct or an indirect variation? So for direct, what we're looking for is the product x times y. That remains constant. And for an inverse variation, that means the quotient y divided by x is constant. Oh boy, I've got that backwards. For a direct variation, our quotient y divided by x remained constant. And for an inverse variation, that's where our product, y times x, remained constant. And again, just working from those relationships that we had on the first slide. So let's look at number 12. Let's try our quotient first, y divided by x. That will show us a direct variation. So I'm going to start with these, like 36 divided by 4 is 9. 90 divided by 10 is 9. And then I would use a calculator to test 13.5 divided by 1.5. Okay, if I do that, I get 9. 22.5 divided by 2.5, that's 9. 67.5 divided by 7.5, that is 9. So since all of those data points, whenever I do y divided by x, that quotient is constant, I know that we have this situation. So for number 12, we have a direct variation because the quotients were constant. All right, let's try the next one, number 14. Well, let's see. Quotient, 16 divided by 4 is 4. 11 divided by 5 is 11 fifths. Okay, so I know it's not direct. Well, let's try the products. 16 times 4 is 64. 11 times 5 is 55. So I know it's not an inverse because the products are not constant. So it's not direct, it's not an inverse. That is neither. So a pretty quick check, we may have to use the calculator just to run through some trials there and see what type of relationship we have. Example 3, this is one that I would probably put a star next to. For whatever reason, this is a very common type of problem. It's probably what I would consider the archetypal problem, the one that when I think of variation problems, this is the type of problem that comes to mind. So we will be told how the two variables vary, and then we'll also be given some sample values that will help us find the k, the constant of variation. And then we have to use that k value to go back and answer a question at the very end. So reading through this, we have an inverse relationship. So I know that y equals k over x. Okay, that's the way that x and y vary. Then I'm told that when x equals -4, y equals -5/4. So I'm going to plug those values in. -5/4 equals k over -4. Okay, and to solve a fraction like this, you may remember from Algebra 1 to cross multiply. So positive 20 equals 4 times k. We find that k equals 5. Or we could have just used some common sense. If I've got -5/4 and I've got something over -4, what must that k be to produce two equal fractions? It has to be a 5. So however we arrive at that k value, that is our first requisite step. Then it says, find y when x equals 3. Well, I know that y equals k over x, and now that I know the k value, y equals that k value of 5 over that x value of 3, and then we would simplify if we needed to. In this case, we do not. Y equals 5/3 is our final answer. Pretty quick problem, provided that we know that we need to follow this y equals k over x template. And our final example, there are relationships between different measurements in the real world that show direct or inverse variation. In this example, we have the average pressure when you're standing on snow compared to the surface area of the bottom of your feet. That's an inverse relationship. We can see that expressed here in the text. Okay, so P varies inversely with the area A. So I know P equals some constant over that area. Okay, so then they'll give us one complete piece of information. Suppose the pressure is 0.43 when you wear the snowshoes that are shown here. So that's some constant over an area of 360. And if we solve for k, we multiply both sides by 360. I find that k equals 154.8. Check my work on that one. Yes, 154.8. And then we need to use that to find what is the pressure when you wear the boots that have an area of 60 inches squared. So now I want to find the pressure. I know it's an inverse relationship, so I know it's k over a. I want to find the pressure. I know the k value is 154.8 based on the information we gathered from the snowshoes. And the area of the boots, 60 square inches, that goes in the denominator. And we find that that pressure is 2.58 pounds per square inch, or PSI. Okay, and let's see if our answer makes sense. Okay, naturally, if we have boots that have a smaller surface area, it's going to produce more force on the snow over a smaller area, so the pressure should be greater. So the fact that we go from 0.43 pounds per square inch to 2.58 pounds per square inch, that makes sense in the context of the problem. We can feel good about that answer. All right, believe it or not, that is the end of section 7.1. This might be a more of a review than anything else on an Algebra 1 concept, but we're trying to lead into this idea where we're working with functions that deal with fractions in them. So kind of opening the door to some work there. Here's a look at your assignment for section 7.1.